the channel, right? My channel. All right, Chemistry 3101. We're going to start with synthesis today. It's the last chapter of Chemistry 3101. And this chapter is mainly a review. So we'll say here, this chapter is mainly a review of chapters 7, 8, 9, and 10. Okay, that's mainly what it is. Okay, does it involve the other chapters? Do you have to know stereochemistry? Of course. You have to know nomenclature? Of course. You have to know pKa's and areo? Yes, absolutely. But I'd say it focuses on these chapters. All right. The chapters 8 and 9, if you go back through all the content we've covered this summer, chapters 8 and 9, those have very specific reactions, hydroboration, oxidation, Markovnikov addition of water, anti-Markovnikov addition of water, bromination, halohydrogen formation, et cetera, where it's just one specific reaction, that you can kind of investigate. Whereas chapter 7 is very different from that, right? Because chapter 7 covers more conceptual reactions, SN1, SN2, E1, and E2, which can't be summarized just, on one page. Well, I guess it could, but anyhow, so that's where you use those tables where it shows primary, secondary, tertiary, alkyl halide, and then we have strong base, weak nucleophile, strong base, strong nucleophile, weak base, and all that kind of thing, okay? And then in chapter 10, we learned allylic bromination in that chapter. We also learned why bromination is more regioselective than chlorination. And yeah, we also looked at the mechanism for hydroboration oxidation. So those are the main topics that we covered in there, but we're going to start out by looking at chapters 8 and 9 in a little more detail here in just a second. And when it talks about a one-step synthesis, okay, so let's say you wanted to take this compound, this is called isobutylene, and let's say you wanted to make this compound, so this would be what, 1,2-dibromo, 2-methyl propane is what you could call this compound. Anyhow, let's say you wanted to do that. Well, you know that you just need one reagent to do a bromination, right? You react with bromine, okay? And you would have to be able to, or you should know how to draw the mechanism of this reaction. You form the bromonium ion and all that kind of thing. And these are the words of the author of our textbook. He says you have to master all the reactions and the reagents required before tackling any multi-step synthesis. So before you can tackle a synthesis that involves 2, 3, 4, however many steps, you've got to master all of the individual reactions. And so we're going to start by looking at question 11.1. It says identify reagents that can be used to do each of the transformations shown here. If you're having trouble with any of these, you notice that the starting material is an alkene. And so where would you find this information? It would be in chapter 8, which is the alkenes chapter. All right, so the alkenes chapter. So we're just going to kind of start and just kind of work our way through these. So what I thought we might do is kind of start here and then work our way partially counterclockwise. So if I want to do this transformation here, where I take this alkene, so the alkene is 1-methyl cyclohexene, and then I want to make 1-bromo, 1-methyl cyclohexane. Well, you can see that that is a Markovnikov addition of HBr across the double bond. So we can put here Markovnikov addition. And so the conditions are just going to be HBr. And of course, I would expect you to be able to draw the mechanism of that reaction. So I'll put a little star by that one there. Right. The next one is going to be an anti-Markovnikov addition. Maybe I'll put a star. Something like that. Anyhow, the next one is anti-Markovnikov addition of HBr. It's not the rich getting richer in hydrogens. It's the carbon that was richer in hydrogens to begin with, namely this carbon, okay, is now taking on the bromine. And so we call this anti-Markovnikov addition. And so we use HBr and an organic peroxide. As far as the mechanism go, it is covered in chapter 10 in gross and gory detail. We went over it last chapter. So you are expected to understand a little bit about how the bromine radical adds first to produce, right? The bromine radical would add to the double bond, and that would give you the most stable radical, right, that I have shown here. And then you do the hydrogen abstraction to get to the final product. But that would be kind of what you would be expected to know about the mechanism for that reaction. Okay, let's see here. What if we did this here? Now, this reaction was not covered in chapter 8, but what if we wanted to take methyl cyclohexane and convert it into 1-bromo, 1-methyl cyclohexane? Could anybody tell me the reaction conditions for this reaction? I want to take an alkane and convert it into an alkyl halide. an alkyl bromide specifically in this case. What would I need to do this reaction? I'm starting with an alkane, and I want to make an alkyl halide. Did anybody tell me what I would use for that reaction? It's a reaction we would have seen in chapter 10. Exactly. We're going to use bromine to do that. Exactly. So we're going to need some bromine and light. There we go. And again, that was covered in chapter 10. So we looked at radical bromination. And then to make the Zaitsev alkene, we're going to use an unhindered base like sodium methoxide or sodium methoxide. Either one is going to give us the Zaitsev product. If we wanted to make the, let's say we wanted to make the Hoffman product, in that case, you'd use a hindered base like potassium T-butoxide, and that would give you this compound here, which is called methylene cyclohexene. No, methylene cyclohexane, sorry. All right, the next one, next reaction, following the order here, so kind of going counterclockwise. This next one, is this a Markovnikov or an anti-Markovnikov addition of water? Could anybody tell me? We're adding water across the double bond, but would it be Markovnikov or anti-Markovnikov? Exactly. Thanks, Isaac. Yep, this is a Markovnikov addition of water across the double bond, and so we're just going to use H3O plus. Now, there's no rearrangement to worry about here, okay? After you form the carbocation, it's tertiary, it's not going to rearrange. But let's say you did have a situation where you had a carbocation that was going to undergo rearrangement and you wanted to avoid that, then you would use oxymercuration, demercuration, and the first step for that would be mercuric acetate, and water, followed by sodium borohydride. So that's oxymercuration, demercuration. It does the same thing, but the only time we use this is when we're trying to avoid a carbocation rearrangement. So we'll put here avoid carbocation rearrangement. Okay, the next one is an anti-Markovnikov addition of water across a double bond. So I'll put a star here because you have to know that. All right, so that's going to be hydroboration oxidation. And the first step is going to be borane, BH3 and THF. And the second step is going to be hydrogen peroxide and sodium hydroxide. All right, good. Next one is just a hydrogenation. We convert the alkene to an alkane. So for that, we use hydrogen gas and palladium, platinum, or nickel. I'll use platinum. You could put palladium, nickel, it doesn't matter. The next one is a halogenation. So for that, we just need bromine. And remember that it passes through the bromonium ion, and you should be able to draw the mechanism for the formation of the bromonium ion. The next one is a halohydrin. So it's very similar to halogenation, except for we use bromine. We use bromine, but now we have a solvent, which is a nucleophilic solvent, or the weak nucleophile, but it's still a nucleophilic, which is water. And water is, the hydroxyl group is always going to end up at the more substituted carbon. It's anti-addition, right? Both of these, actually all of these ones here are anti-addition. And so the hydroxyl is going to be on one face of the molecule and the bromine is going to be on the other face of the molecule. Oops, I lost my oxygen there. And I would think you should be able to draw the mechanism of that. If you can draw the mechanism of bromination, you can draw the mechanism of halohydrin formation. Okay, moving on, we have dihydroxylation. So we have anti-dihydroxylation, and then we have syn dihydroxylation. Well, if we want to do anti-dihydroxylation, it's two steps. The first step is going to be MCPBA, and the second step is going to be H3O plus. I only expect you to be able to do the mechanism for the second part, okay, not the first part. But remember, when we write down something like MCPBA, which is metachloroperbenzoic acid, you can write RCO3H because there's another peroxy acid that's shown in the textbook that will also affect this transformation. It's a peroxyacetic acid, okay? The next one is going to be a syn dihydroxylation. And so for that, we learned a plethora of ways of doing it. We learned osmium tetroxide, followed by sodium bisulfite or sodium sulfite. We learned potassium permanganate. But I think the best way to do it is to use a catalytic amount. So osmium tetroxide, we'll just put cat for catalytic amount, and NMO, N-methylmorpholine N oxide, which is the co-oxidant. I guess I could have used a different color for that one, just to be consistent. There we go. All right, and the last one is ozonolysis. So we break apart our alkene, our double bond. And so for that, we're going to need ozone in the first step. Come on. Ozone. And then in the second step, you can use DMS. DMS. And just so you're aware, in the textbook, it says DMS, or you can use zinc and water. Okay. So you have a suspension of zinc powder in water. Either one is totally acceptable to do that. All right. So I think that covers all of the reactions that we would have gone over in Chapter 8. I highlighted the mechanisms that you have to know in this chapter. I guess there's a couple that I left. There's one that I left, or two that I left out. Okay, so you should know how to do an elimination. That's covered in Chapter 7. And you should know how to do this elimination as well. But I recommend taking this sheet and printing it out, and printing out a few blank copies of it, and then just trying to do it over and over and over until you've mastered each one of the reactions. Well, that is part of the reactions, so only a part of the reactions we've learned this semester. We also learned one-step syntheses. Come on. I don't know why that's highlighted, but anyhow. All right, we'll just leave it the way it is. We also learned one-step syntheses for alkynes. Okay, so this question says, identify the reagents that can be used to do each of the following transformations. If you're having trouble, the reagents can be found in Chapter 9. So Chapter 9 was the alkynes chapter. And so you should try to identify the reagents yourself without help. Okay, it's a very good thing to study without peeking at the solutions manual or the textbook or something. Okay, you want to be able to do it without any assistance. All right, so let's start here. This first reaction here, if we start at 12 o'clock, the one that's pointing straight out. Well, here you can see it's a Markovnikov addition of the addition of HBr across the triple bond. But here you can see it's only been added once. And so for that, we would just put HBr. So we'll just put HBr, and we'll put one equivalent of HBr. So one equivalent of HBr. And what it means by one equivalent is if you have one mole of this, you're going to add 1 mole of HBr. That's what one equivalent refers to. So now if you want to do another Markovnikov addition, you can just put HBr. I mean, it's taken for granted that it's going to be a stoichiometric amount. So HBr totally works fine. And something that's not shown in here, but I'll add it, is if you wanted to go straight from here to here, you could if you just write excess HBr, right? Then it's going to keep adding and adding. And these are the mechanisms that aren't, or these mechanisms aren't that well understood as discussed in the textbook. And so I don't expect you to be able to draw a mechanism for that. However, I do expect you to be able to draw these mechanisms here. Whether you have a geminal dihalide or a vicinal dihalide, you should be able to go to the alkyne. And that is a two-step process, right? The first step is excess sodium amide, and the second step is water, right? First step is excess sodium amide, and the second step is water, and that gives us our terminal alkyne here. Okay, next one, if we're doing an ozonolysis reaction, it's very similar to the ozonolysis of an alkene, in that the first step is ozone, but the second step is going to be water when we're dealing with an alkyne. The next one is, you can see, it's just polyhalogenation. I mean, you're halogenating the heck out of this thing, pardon my language. So you'll just put here excess bromine, just halogenate everything. Whereas if you only want to add 1 molecule of bromine, well, in that case, you would write specifically 1 equivalent of bromine. Okay, next one is one of the most important reactions that we learn in this entire chapter. We're adding a carbon onto the molecule. And so the first step is going to be sodium amide, and the second step is going to be methyl iodide, like that. All right. The next one, we take the triple bond and we're reducing it to the alkane. So I'm talking about this reaction here. That's the same reaction we saw in the previous slide where it's just hydrogen, palladium, platinum, or nickel. I'll use nickel. If you want to make a cis-alkene, in that case, you have to use Lindlar's catalyst. So I'll put H2 Lindlar's catalyst, or sometimes they'll say the P2 catalyst. Okay, either one is totally fine. But if you want to make the trans alkene, in that case, you have to use sodium metal reduction in liquid ammonia. Like that, you get the radical anion. And then the radical anion, of course, is what produces the trans alkene. Okay, these next two here are really important because you have to understand what's going on here in terms of, is this a Markovnikov or anti-Markovnikov addition? But you should also understand the enol that's produced. So the first one, when we take this terminal alkyne and we end up with an aldehyde, okay, we end up with an aldehyde, that's the result of an anti-Markovnikov addition of water across that triple bond. So we end up with this intermediate, okay, this enol, and then that enol is going to undergo tautomerization to give you the aldehyde. And so in this case, we use 9-BBN in the first step, and then the second step we use H2O2 and sodium hydroxide. Whereas in the next one, if we want to make the methyl ketone, the enol we're going to produce in this case would be this one here, okay, and that's going to undergo tautomerization to give you the methyl ketone. So for a Markovnikov addition of water, you not only need sulfuric acid and water, you also need mercury 2 sulfate or mercuric sulfate. You need all three of these to get the final product. All right, and just so you're aware, if you write 9-BBN, there's nothing wrong with that, but you could put R2BH, or like I told you, MCAT sometimes uses this kind of thing. ACS does too. All right, where they draw something like that. Or you can say, or dicyamylborine was another one that we looked at. So in terms of mechanisms here, I'll just use the red star here. I mean, what are the mechanisms? You should be able to draw these two mechanisms here, okay, for the double elimination, deprotonation, then protonation. You should be able to draw this mechanism for the deprotonation and SN2 reaction. Those are the main ones. I guess the mechanism of tautomerization, whether it's in base or whether it's in acid, you should be able to draw those mechanisms too. Those would be the main ones from this chapter. So there you go. That's a lot of information. And it took us a long time to learn all of those reactions. But that covers chapter 9. So chapter 8 and chapter 9. And I'm not trying to sound like a meanie or intimidating or anything. Trust me, I think I'm very supportive of my students, but there can't be any hesitation on these. Okay, you don't want to get out a quiz or an exam, say, oh, what was hydroboration oxidation again, or how do I do this transformation? You need to be able to recall them with relative ease. Okay, relative ease, so that you don't spend too much time, going over the same thing again and again. So, sometimes we can think about functional group transformations. Now, an alkyl halide, as far as a functional group goes, what's kind of cool is that using the tools that we have from chapter 7 and chapter 8, we're actually able to move a halogen around a molecule. Like, let's say you want to take this bromine, right? This is a secondary alkyl halide, and then you wanted to convert it to this tertiary alkyl halide. Well, you guys know that if you take it and you if you start with this this compound and you treat it with an unhindered base like sodium methoxide or sodium methoxide, it doesn't matter. You're going to end up forming the Zaitsev alkene, right? And then you could do a Markovnikov addition of HBr, okay? And that is going to give you the tertiary alkyl halide. So let's say you couldn't buy this compound, but you have this compound. Well, then you just do a couple of reactions and you can make it. And this is kind of the mindset of an organic chemist is, what can I make? What's something new that I could do here, right? Trying to push the frontiers of science. So it says we can lay out all the reactions we know where alkyl bromides and alkenes are concerned, then figure out the reagents needed to kind of move the bromine around. So we just looked at this one here, going from here to here. Now, what if you made a mistake? Hopefully you wouldn't do this, but what if you did this reaction right here, and then you said, oh, fiddlesticks, I made this alkene, but I didn't want to make that. I need to go back to my original starting material. Well, in that case, you could do an anti-Markovnikov addition. Or what if you wanted to move the bromine down to this carbon? Well, in that case, you'd make the Hoffman you'd make the Hoffman alkene, right? This is the Zaitsev up here. And then you would just do an anti-Markovnikov addition of HBr with peroxide. So we have a lot of power in our ability to move a halogen around a molecule. And what's so great about this, and this, they're all just alkyl halides. But what's so great about that? We spent all of chapter 7 pretty much talking about alkyl halides, right? So we talked about SN2, SN1, E1, and E2. So there's a lot of possibilities here with alkyl halides. It's very cool. Now, what if you have an alcohol? Also in chapter 7, we learned a way to take an alcohol, which is a very poor leaving group, thumbs down, okay? And then we make it into a tosylate. So after the first step, you would end up with this. They didn't put it on here, so I'll just draw it here. OTS. They'll put here, good leaving group, you know? So we'll put a thumbs up next to that one. So you can take something that's even a poor leaving group and just through one quick reaction with tosyl chloride and pyridine, now you've got a good leaving group, and you can treat this exactly like an alkyl halide, right? So now you can make a Zaitsev alkene, or you could make a Hoffman alkene, right? Then you can do hydration, a Markovnikov hydration. You could do, let's say you made a mistake here, but God forbid, okay, you could do an anti-Markovnikov addition of water, which we went over a couple of slides ago. Let's say you had this compound here. This is a great example because we haven't talked much about oxymercuration, demercuration today, right? If you were to just do a hydration on this guy, I don't have a lot of room here, but let's say you just tried to treat this guy with H3O+, okay? What you're going to end up, I'll put H3O+ here. You're going to end up with this carbocation, right? But that's going to undergo a hydride shift. So if you want to avoid that, in that case, you have to use oxymercuration, demercuration, right? Avoid carbocation rearrangement. Okay, so very cool again. And just to kind of whet your appetite for Chemistry 3111, for those of you who are enrolled in the class in the fall, you know, the first new chapter, the first bunch of new material we're going to learn is alcohol chemistry. So that's going to be covered in chapter 12. We have a whole chapter devoted to alcohol this and alcohol that. So you already know how to move a hydroxyl group around a compound. So that's kind of cool already. Let's see here. What else? Let's say you want to move a double bond. Okay, we did this quite a bit this semester, where we took a substituted alkene and then we made a less substituted alkene. So you guys know how to do a Markovnikov addition of HBr, right? The rich getting richer. Now I have a tertiary alkyl halide, and I can treat this with a big old hindered base like DBU, DBN, potassium T-butoxide, right? And now I can make this less substituted alkene. And if you're sitting there going, what's so great about this? Well, what did we discuss alkenes? I mean, we did a whole chapter. Chapter 8 was that we just covered the question, 11.1. It was alkenes this and alkenes that. So again, we have a lot of power in our ability to move double bonds around a molecule. We could even put the double bond down here if we do an anti-Markovnikov addition of HBr and then treat with a strong base, right? We're going to pull off this proton here, right? So our T-butoxide, not asking for a mechanism or anything, but it's going to pull off this proton, and we're going to end up with, you know, this compound here. So again, but and again, this is not me trying to be brash or rude or anything like that, but these are the words of the author of our textbook, David Klein. So if you won't take my word for it, take his. I mean, this guy's a brilliant chemist and a great teacher, and he says we have no chance to get this far unless we can easily recall all the possible reagents and reaction conditions first. You know, it says here easily. So I always say with relative ease, so it doesn't sound so bad. But I agree with him. You know, you have to be pretty quick on your toes on these reactions that we've seen. And let's face it, we've seen them more than once this semester. We've seen them a few times. Oops. All right. So let's see here. Now, what we're able to do is move, you know, convert a triple bond to a double bond, a double to a triple, right? Double to a single. And now we've learned this one in chapter 10, how to convert a single bond into a double bond, right? By bromination and then an elimination. So there's so much opportunity here to go between alkane, alkene, alkene to alkyne, right? We learned all kinds of reactions with alkenes. We learned all kinds of reactions with alkynes. As far as alkanes go, yes, they are covered in chapter 4, but as far as their reactions go, that's more bromination. That's covered in chapter 10. So there's a lot of opportunity here. Okay, So what I'm going to do is I wanted to walk through some of these problems with you. These ones aren't very long, and we looked at some of these already, I think. So I won't spend a ton of time on these, but if we want to go from a double bond to a triple bond, okay, just going from a double to a triple. Well, we know that the only way we have to make a triple bond, right, since there's no change in the carbon skeleton here, I have, what is it, 6 carbons and 6 carbons. That means I have to have this compound. I have to have this, this geminal dihalide, like that, right? Then I do a double elimination with excess sodium amide followed by treatment with water, and there you go. You've got your alkyne. So how do I go from here to here? Well, the answer is step 1 is going to be just some bromine to make the dibromide. Then step 2 is going to be excess sodium amide. You end up with an alkanide after that step. And so step 3 is just to put water on it. And there you go. You're done. Okay, so it's a 3-step process. Now, what about this one here? If I want to take this primary alkyl halide and I want to make this tertiary alkyl halide, well, the retrosynthesis here is that, let me use a different color, is that I've got to make this, the methylene cyclohexane that we discussed earlier on. It looks like this, okay, in order to do a Markov-Nikov addition on it. And we know that there's only one beta proton, right? If this is our alpha carbon, this is our beta. There's only one beta proton here. I don't want to do a substitution here. I want to do an elimination reaction. And so I don't want to use a base like sodium ethoxide or sodium methoxide because that's going to do an SN2 here, right? I want to use a big bulky base like DBN or DBU or T-butoxide because that's going to suppress any SN2. And so we're going to put potassium T-butoxide. And again, if you wanted to put DBU, DBN, that's totally fine. And so that would give us the alkene. And so then all we have to do is a Markov-Nikov addition of HBr. So just a 2-step process here. The next two look kind of similar, don't they? Because we can get from here to here pretty quickly, or actually from here to here. But anyhow, I digress. Let's see here. So if we want to take this exocyclic double bond and make the internal double bond, right, what we're going to need in that case is we're going to have to have the 1-bromo, 1-methyl cyclohexane, and then we can treat that with an unhindered base, and that will give us the Zaitsev alkene, which is this alkene here. So our step 1 is going to be HBr, and our step 2 is going to be to use an unhindered base like sodium methoxide or sodium ethoxide, and you're done. There is another way to do this one, though. Does anybody know another way to do this one, or did anybody solve this one a different way before class or anything? I'll put it over here. There is another way, okay? Where's my pen? There we go. Like this, this, and this. There is another way that's even more elegant, in my opinion, and that is if you want to go from here to here, let me do it like this. The first thing you would do is treat it with aqueous acid, and that would give you the Markov-Nikov addition of water, so you'd end up with this tertiary alcohol. And then all you have to do is treat it with concentrated sulfuric acid, so conc H2SO4, and heat it up. And the concentrated acid is going to drive off water, but you make the most substituted alkene. So either one works. I like the second one. It's prettier, but again, they're both equally fine, okay? Okay, last one. Let's see. We know the first step has to be to add a bromine here, so using bromination. So if we had this compound, the 1-bromo, 1-methyl cyclohexane, then I just treat it with an unhindered base. So step 1 is going to be bromine and light, and step 2 is going to be sodium. I'll choose ethoxide this time just to be more interesting. All right, everybody, give me a thumbs up if you're like mostly confident on these transformations that we've looked to up to this point today. So really what I'm asking for is, are you really confident on question 11.2 and 11.1? Cool. All right, great. You want to make sure you have these mastered, you know, and it makes the class so much more enjoyable, and it gives you a better grade, of course, you know, but it makes the class more relaxing as you move forward. So now, like I told you Avogadro's number of times this semester, How do you win a Nobel Prize in organic chemistry? Find a way to make carbon-carbon bonds. And so when we talk about changing the carbon skeleton, it actually refers to adding carbons, but it also refers to removing carbons. And really, as far as adding carbons goes, the only thing we have is step 1 is going to be sodium amide. Step 2 is going to be some kind of alkyl halide. And that's when we start with a terminal alkyne, right? That's all we've got so far is to do this. So I'll just put R, right? That's the only thing we have. And then when it comes to removing carbons, the only thing we have is ozonolysis, is ozonolysis of an alkene or an alkyne. That's literally all we have for reactions here, okay? In organic chemistry too, yeah, we learn a whole bunch of new ways to make carbon-carbon bonds. But so far, it says here, most of the reactions that we've learned only involve changes of functional groups. In moving the location, they don't involve changing the carbon skeleton. So again, hear the sound of my voice, my friends. We've only learned one way to increase the number of carbons in a molecule, and that is to take a terminal alkanide or acetylide and do an SN2, right? Just do an SN2 reaction on a primary or methyl alkyl halide, and that's it. That's all we've got. It's the only thing. Again, later on, we'll look at a whole bunch of cool ways to do this. But so far, if you see a bigger carbon skeleton, it means that this reaction or something like this has to have taken place. Similarly, if you start with, let's say, 5 carbons and then you end up with 4, well, the only way you can do that in this class that we've learned is to use ozonolysis. Of course, if it's an alkyne, right, for an alkyne, we just went over this, it's going to be step 1 will be ozone, step 2 will be water, okay? And in this case, you'll end up with, you'll end up with 2 carboxylic acids, I guess, in this specific case. But that's the idea. That's all we have. And so let's say we wanted to do this first transformation. We're taking the simplest possible alkyne, which is called acetylene, and then we want to add a methyl group on one side and an ethyl group on the other. Can anybody tell me, does it matter which one of these groups I add first? If I add the methyl group first or the ethyl group first? No, exactly. Like Isaac said, it doesn't matter at all. So let's add the ethyl group first. I don't know, E comes first in the alphabet. So we're going to start out with acetylene. Step 1, sodium amide. Step 2, ethyl iodide. And we're going to end up with 1-butyne. Then step 1 is going to be sodium amide. Step 2 is going to be methyl iodide this time. And now we end up with our final product. All right, the next one is kind of reversed, right? It's inverted because here they gave you the alkyl halide and then they want you to add these 2 carbons. So for this one, you can just assume that you have a reagent like sodium acetylide. It's a commercially available reagent. And so you just buy that. It's going to do the SN2 and you're done. So it's literally one thing. It's just some sodium acetylide and you're finished. Okay. Now, how do you approach a synthesis problem? I don't know, scream, run around the room. No, I'm kidding. There's a number of ways you can do it. I'll be honest with you guys. I mean, when I'm solving a synthesis problem, if it's something that I think that is doable for me at my skill level, I'll usually just go for the lowest hanging fruit, like if there's a change in functional group that I think is really abundantly clear, I'll start working with that. Or if there's a change in the carbon skeleton, I'll go with that. But this is the David Klein method. As he said, always start by looking at the carbon skeleton. And it's usually abundantly clear if there's no change, okay? But if there's a change, then, you start thinking back to, okay, if I'm adding carbons, I've only got one possibility. If I'm removing carbons, I've only got one possibility. Then he says, start looking at the functional group. Is it an alcohol? Is it an alkyl halide? Do I have a ketone? Or sorry, ketone, an aldehyde, right, from Markovnikov or anti-Markovnikov addition across a terminal alkyne. Is there a triple bond? Is there a double bond? And solving synthesis problems involves recalling all of the reactions that are learned and working through many examples. And, if you talk to somebody who works, as an organic chemist by trade, like I did, for a long time, you talk to a chemist, and this is not a joke, I'm not making this up, there's something that all organic chemists call their toolbox, which is kind of like the nether regions of the brain, where it has all the reactions that they know, which is not every reaction, but would be a lot of reactions. You know, and then they can recall those quickly, and then be able to apply them to a problem. And so the only way to get good at it is to work through many, many examples. It goes back to my analogy of riding a bicycle or playing the guitar or whatever. You can watch somebody play the guitar all day, all year, for years, but it doesn't mean you can play it, okay? To get good at it, you've got to try it, and you got to make mistakes along the way. And the same thing goes with riding a bicycle. So do not be afraid to make mistakes. So let's say you had a problem like this. Let's say you were on a quiz and you had this compound here. So you count the carbons. You have 1, 2, 3, 4, 5. We're really taking the Klein approach here. So 5 carbons. And then we have 1, 2, 3, 4, 5, 6, 7. So we're adding 2 carbons. So we go from 5 carbons to 7 carbons. Okay, so that's the way he does it. He just always starts with this counting thing. Okay, well, you can clearly see there's a change here. And so we have that terminal alkyne proton, right? So step 1 is going to be sodium amide, and we only need to add 2 carbons on the end. So step 2 is going to be ethyl iodide, like that. And there you go. So that's the kind of way you want to approach these kinds of problems, and he has the answer here. Now let's say you wanted to reduce it to the transalkene, right? You've got to know the transalkene is sodium metal reduction. You've got to know the cisalkene is hydrogenation with Lindlar's catalyst, all that good stuff. Another thing, and this is something that I don't see a big problem with by the time we get to the end of this class, but let's say you're taking 3111 with me in the fall and we're writing a paper quiz or something. One thing you don't want to forget to do is you never want to just put your reaction arrow and then just say, okay, well, first step is sodium amide and then ethyl iodide, and then I'll do the reduction with sodium and ammonia, right? This means nothing. This is literally throwing, what this implies is that you're mixing sodium amide, ethyl iodide, and sodium metal, okay? That's not going to give you anything but a soup, maybe a fire or something. So it's a very bad idea. And so, bad idea, right? You've got to number each step, so don't forget that. First you have your base, then you have your electrophile, then you have your reducing agent, right? Again, not a mega problem with my students, but he puts it in here just as a reminder, I think. So let's say we wanted to do some of these transformations here, okay? You can see that in the first one, we're going from 1, 2, 3, 4, 5 carbons to a total of 1, 2, 3, 4, 5, 6, 7, 8. And the next one, you can just count the carbons on the top because you can see this geminal dimethyl is down here. So you can say 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, which is kind of interesting. So you're adding a total of 3 carbons on there. And then the next one, same kind of rationale. You see this methyl group down here. And so you can kind of count 1, 2, 3, 4. And here we have 1, 2, 3, 4, 5, 6. So something I'm going to ask you to do right now is, if you're in class with me right now live, we're going to pause for just a minute. And even if you're watching this video, if you want to get good at organic chemistry, what I would recommend doing, getting a blank piece of paper, pausing the videos, whatever, and write these problems down and try them, and see. And then once you think let's say you can do the first one with relative ease, see if you can do the second one without looking at anything, And the second one is a little more difficult, okay? But remember, to solve this one here, what I would tell you is that, remember I told you that you can assume that you have sodium acetylide, this ionic, compound here. You can also assume that you have other little acetylides, like, the propyne conjugate base or the butane, right? If it's something small, you can assume that you have reagents like this and that they are commercially available. So keep that in your pocket, okay? Because you might need something like this or something like this to solve a couple of the problems in here. Okay, so what I want to do